Hi. I've shown you what the AdaBoost algorithm is and shown you an example of how it works, but you might still feel uneasy. This is all very mysterious. How did it work? So you can go to the proofs and that will give you some intuition, but you can gain a nice intuition by considering AdaBoost as a gradient descent algorithm. So we have used gradient descent for minimizing functions, for finding the optimum. And what we're going to do here is try to find an optimum of a function, which is the prediction function, the sum of the weak learners. So what that is called variational optimization. So variational optimization is essentially very similar to gradient descent, but the space of things that you're working on, rather than working on vectors of some dimension d, these are vectors of infinite dimension or functions. You can think about something like the shape of the wing of an airplane as being a continuous function that you want to optimize for some goal, let's say to minimize drag or to maximize lift. Okay, so you would use variational optimization methods to do that. And basically, it is just like gradient descent. It's just that the derivatives are now derivatives over functions. So we have x, that is our input, and we have y, that is our output, +1 and -1. And we have a training set which has particular x's and labels, +1 or -1. Okay, so here are the plus examples, and here are the minus examples. And what we want to do is basically find a function that will be minus when it's mostly minuses, and will be plus when it's mostly pluses, right? But we have only a finite number of examples, so we have some ambiguity about how we want to do it. So let's see how this becomes a variational problem. So suppose that we have a strong rule that we got so far, and we want to improve on it. So the strong rule maybe looks something like this. Okay, so it's negative here, and it's positive here, but here it's not quite as positive as we would like it to be. So the HT, the weak rule, you can think about it as an update to the function, something that you add to the function in order to improve it, in order to make it fit the data better. So let's say that one function that we might want to use is this one, HT, the red function, and that basically will do just the right thing of improving, pushing just this part of the function up without changing this part of the function, which is already good. So if we look at this as a variational optimization, we're basically thinking about what coefficient to put in front of this function. So if we put 0, then it doesn't change the function at all. If we put 0.4, then it changes the function this much. If we do 0.8, it changes the function this much, right? So we're changing the function continuously by changing this weight. And by that way, we're trying to get it to be the correct function that we want. Of course, the correct really function that we want is just a decision, but that's a function that is kind of hard to optimize. So we're using something a little bit different. So at this point, I want to introduce the margins. Margins are going to be useful for many things, and now I'm just going to define them. So suppose that we have some fixed set of weak rule, just h1 to h big T, and we are fixing them. And now we're thinking about the example xi just as the outputs of all of these rules. Okay, so it's just the output from each one of the rules. And then you have the label that is +1 or -1, and you have the training set. And the goal is to find a good weight that minimizes the number of training mistakes. So here we have a plot where the examples represent HI, so the mapping that the H's H1 and H2 give to these examples. And each example is also labeled by the label yi. Okay, so you see that this vector alpha is pretty good in terms of classification because it just makes an error here on that example and here on that example. Okay, so if we use this weight alpha to multiply the HIs, then we would get a good classifier. Now, it's a little bit tricky to think about it this way, so to make it a little bit easier, we're going to reflect the examples that are negative. So we're going to reflect them through the origin, and basically now we have, instead of being a side that is predicted plus and a side that is predicted minus, we have a side that is predicted correctly and a side that is predicted incorrectly. Okay? And so we see here that these are the two mistakes that we made. And so now we can project and just look at the distribution of these values. So this thing that we got here is called the margin. And if we project it on, so this margin is if we project it on a particular alpha. Okay, so we have this alpha, and we project all of the examples on it. And we see that most of the examples are on the correct side, on this side. And there are two examples on the incorrect side. So that basically tells us that this is a pretty good classifier. But if we wanted to do anything, we would want these to stay on this side and these to go to that side also. Okay? So this is always going to be a one-dimensional plot, but this is really just a simplification. This here is two-dimensional, but typically we have thousands of weak rules. So when we talk about margin, we really get this meaningful projection that we can actually look at. So we saw how the margin is defined. Now let's see a little bit more how the margin relates to AdaBoost. So we have the margin distribution here. Okay, so these are the examples whose prediction with the weights alpha is correct. And these are the examples whose prediction with the weights alpha is incorrect. And what we're interested in at the end of the day is to minimize the number of mistakes. So basically, we would like to minimize this step function, which is 1 for the mistakes and 0 for correct ones. But this is a function that is very hard to work with. It's very hard to say what kind of small change do I need to make in order to minimize that function, because only examples that are right here on the boundary will actually make any difference if you do small steps. So what we're doing instead is that we're putting upper bound on this function, a smooth upper bound that is e to the minus the margin. And this function is relatively easy to minimize. It's a convex function. It's an easy function to minimize. And it's not exactly what we want, but it's an upper bound on what we want. So if we can make this function small, then necessarily we're also making this function small. So we want to see now how this potential or loss function that we defined, the exponential loss, gives us a gradient descent algorithm. So the basic idea is that we're adding the rules one at a time. So each rule is basically a gradient step. And we're fixing the rules before. Okay, so we're not changing the weights on the rules from before. And the weak rule defines how each example should move to increase or decrease the margin. So what we're showing here is how each example would move. It will move in the direction of correct or direction of incorrect. That depends on the weak hypothesis. And here we also allow the weak hypothesis to sometimes give bigger predictions and sometimes give smaller predictions. They don't have to all be -1 or 1. They can be any number between. And so now we want to say, okay, if we add this rule with some weight, how much will it change the potential, right? So it will change the potential. The change in the potential is basically a sum of these little gradients, right? So each example has a gradient that depends on essentially the slope or the derivative of the potential function at this point. And that is exactly the weight function, the weights that we give to the examples. So examples that have high weight are examples that are on the bad side of the margin, on the incorrect side. And here is some of the math to describe that you can go on and watch offline. So there are different potential functions that have been devised. One is AdaBoost that has a loss and a weight that are both exponential. And then there is LogitBoost that was defined as gentle boost by Hasty, Friedman, and Tibshirani. And in this case, the potential function is log of 1 plus e to the minus the margin. And the weights that you get are basically going like this logit function. Okay, so because the derivative here of the LogitBoost goes just to 1, then the weights are bounded by 1. So there is not conclusive evidence, but there is some evidence that AdaBoost is better algorithm when you have a decision boundary that gives you close to 0 error. And LogitBoost is better when the amount of error is significant. There is a way of looking at all of this in a combined framework, which is called AnyBoost or gradient boost. And this is a general recipe for learning by incremental optimization. Okay, so it applies to any differentiable loss function. And what you basically do is you define the weights of the examples according to the gradient of this loss function. Each iteration, you calculate the weights. You find a step that decreases the total weight, and then you update the rule that you have according to by multiplying the update, the weak rule, with this alpha t. And methods like gradient boosted trees, that's basically what they do. So to summarize, the margin measures the correctness of the prediction, and boosting can be viewed as gradient descent over the loss function that is defined on the margin. And there are various loss functions that are popular. There is AdaBoost that is exponential, LogitBoost that is a logistic function, and MadaBoost, which is basically clipped exponential for the weights. So each one of them has its own slightly different properties, but overall they all behave pretty similarly. I'll see you next time.